below. In this lecture we will find the area of the green shape in 3 different ways. In the drawing we have a circle. We know that the radius of this circle equals to 5 units, and we also have the green shape. We know that angle ACB equals to 60 degrees, and we also know that AC, line segment AC is tangent, or the tangent AC is tangent to the circle at point A, and CB is tangent to the circle at point B, and we want to find out the area of the green shape. So we start with the first method, and first of all we will define the center of the circle as point O. Then we will join together points A and O by a straight line. And we will join together points B and O by a straight line. Actually, AO is the radius of the circle that equals to 5 units, because of the fact that line segment AO starts from the center of the circle, that is to say from point O, and ends at point A, that is on a point on the circle itself. Therefore AO is the radius of the circle that equals to 5 units, and from the same reason OB is also the radius of this circle that equals to 5 units according to what is given in the question. Okay, and we actually have a rule that states that we know that AC and CB are tangent to the circle at points A and B. So if we have a circle and this is the center of the circle, and we have tangent to this circle at point X, and we have radius of the circle that is drawn to the point of tangency, that is to say to point X. Then the rule states that a tangent to the circle, that is to say BX, a tangent to the circle, tangent BX is tangent to this circle at point X. This is the point of tangency. The rule states that a tangent to the circle is perpendicular to the radius drawn to its tangency. So I will read the rule again. The rule states that a tangent to the circle is perpendicular to the radius drawn to its tangency. So actually we have here tangent bx, that is tangent to this circle at point x, and according to this rule, this tangent to the circle is perpendicular to this radius that is drawn to its tangency. Actually, this radius is drawn to the point of tangency, and it is actually touches the point of tangency x. This radius touches point x. So it is drawn to the point of tangency. Therefore, this tangent is perpendicular to the radius. That is to say, this angle equals to 90 degrees. Okay, again, whenever you have a tangent to the circle and a radius that is drawn to the point of tangency, then the tangent will be perpendicular to the radius. We have tangent bx, the point of tangency is point x, and the radius is drawn to the point of tangency. Actually, it touches the point of tangency, that is to say point x. Therefore, this tangent bx is perpendicular to this radius, that is to say this angle equals to 90 degrees. Okay, so actually, according to the rule that I stated, we have CB is tangent to this circle at point B, and the radius is drawn to the point of tangency. Therefore, the tangent is perpendicular to this radius, that is to say this angle equals to 90 degrees. And the same rule applies here. We have tangent CA, that is tangent to this circle at point A. Therefore, the tangent CA is perpendicular to this radius that is drawn to the point of tangency, as actually this radius touches the point of tangency. Therefore, the tangent CA is perpendicular to this radius, that is to say this angle equals to 90 degrees. Okay? And we have second rule. The rule actually called two tangents theorem. Two tangents theorem. Actually, two tangents theorem states that the lengths of two tangents from a common external point to a circle are equal. So I will read the two tangents theorem again. Two tangents theorem states that the lengths of two tangents from a common external point to a circle are equal. So actually, if we have a common external point, that is to say point P is external point in relation to this circle, and from this common external point we draw two tangents to this circle. This is the first tangent. So this tangent is tangent to the circle at point S, and we draw also the second tangent from point P to the circle. This is the second tangent. The touching point between this tangent to the circle will be defined as point M. Then, according to two tangents theorem, the lengths of two tangents from a common external point to a circle are equal. So the length of this tangent SP is equal to the length of the other tangent, that is PM. PM equals to SP. So those two lengths are equal to each other because of the fact that they exist from a common external point, that is to say from point P. They both exist from point P and both are tangents to the same circle. Therefore, the lengths of those two tangents are equal to each other, that is to say SP equals to PM. Okay, so according to the two tangents theorem, we have here external point to this circle, that is to say point C is an external common point in relation to this circle, and from point C we have two tangents to the circle, tangent CB and tangent CA. Therefore, according to the two tangents theorem, CB equals to CA. So the length of CB equals to the length of AC. Okay. So I will write down that CA equals to CB according to two tangents theorem. CA equals to CB according to two tangents theorem. Okay. Line segment CA equals to CB according to two tangents theorem. Okay, and in the next step we will join together points O and C by a straight line. And we will focus on triangles AOC and BOC. Okay, in triangles AOC and triangle BOC. Okay, so we will focus on triangles AOC and triangle BOC. On those two triangles, BO equals to AO. Both of those two line segments are the radiuses of this circle. So BO equals to AO. Both of them are equal to the radius of this circle that equals to 5 units. Okay? So BO from triangle BOC is equals to AO from triangle AOC. And also we have already proved that BC equals to AC according to two tangents theorem. BC equals to AC according to two tangents theorem. Okay, BC equals to AC according to two tangents theorem, and we have common side. OC belongs to both triangles. OC belongs to triangle AOC and OC also belongs to triangle BOC. So OC equals to OC. Okay, OC equals to OC. It is a common side. It belongs to both triangles. Actually, we proved that all the sides of triangle AOB, AOC are equal to all the sides of triangle OBC. So we actually proved that triangle AOC is congruent to triangle BOC okay, we proved that triangle AOC is congruent to triangle BOC according to side rule. Okay, so those two triangles congruent to each other according to side rule. So what is side rule? Side rule states that if you prove that all the sides of one triangle congruent to all the sides of another triangle, then those two triangles congruent to each other according to side rule. Okay? From the fact that triangle AOC congruent to triangle BOC, we can derive that angle BCO equals to angle ACO. And this is according to the rule that corresponding angles in congruent triangles are equal to each other. Corresponding angles in congruent triangles are equal to each other. Again, angle BCO equals to angle ACO according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define angle ACO as x, then angle BCO will be also equal to x. Okay? And we know that x plus x equals to 60 degrees. So 2x equals to 60 degrees because angle BCA equals to 60 degrees. Okay? 2x equals to 60 degrees, and if we divide this equality by 2, we will get that x equals to 30 degrees. X equals to 30 degrees. That is to say, angle BCO equals to 30 degrees, and angle ACO also equal to 30 degrees. Okay? So actually we have here in triangle, we will focus on triangle. First of all, we have a rule that states that the sum of the angles inside a quadrilateral equals to 360 degrees. So I will write down the rule. The rule states that the sum of the angles inside a quadrilateral equals to 360 degrees. So I will read the rule again. The rule states that the sum of the angles inside a quadrilateral equals to 360 degrees. So actually, according to that rule, the sum of the angles in quadrilateral ABCO equals to 360 degrees. Therefore, here we have 60 degrees plus 90 degrees plus 90 degrees plus the side of angle AOB must equal to 360 degrees according to the rule that is stated. Again, according to the rule that I stated, the sum of the angles in quadrilateral ABCO equals to 360 degrees. So here we have 60 degrees plus 90 degrees plus 90 degrees equals to 240 degrees. So we will subtract 240 degrees from this equality, and we will get that angle AOB equals to 360 degrees minus 240 degrees equals to 120 degrees. Okay, so angle AOB equals to 120 degrees. So this angle equals to 120 degrees. Okay. So in the next step, we will focus on the right triangle, triangle AOC. Triangle AOC is a right triangle because angle OACO equals to 90 degrees. This angle equals to 90 degrees. So in the right triangle, triangle AOC, we know that tangents 30 degrees equals to AO over AC. Again, in the right triangle AOC, tangents 30 degrees equals to AO over AC. But what is the size of AO? AO equals to 5 units. It is the radius of this circle. So we substitute AO by 5 over AC. Okay, tangents 30 degrees equals to 5 over AC. We know that the value of tangents OC is 1 over root 3. So we substitute tangents 30 degrees by 1 over root 3. So 1 over root 3 equals to 5 over AC. Here we will multiply this equality by AC. We'll get that AC over root 3 equals to 5. So here we will multiply this equality by root 3. And we will get that AC equals to 5 times root 3. Okay, AC equals to 5 times root 3. So we can write here that AC equals to 5 times root 3, and AC equals to BC, so BC also equals to 5 times root 3. And what is the area of triangle AOC? So this is the sign of the area. This means the area of triangle AOC. So the area of triangle AOC will be equal to the base of the triangle times the height to the base divided by 2. The area of triangle AOC equals to the base of triangle AOC times the height to the base divided by 2. The base is AO. Times the height is AC over 2. So the area of triangle AOC equals to AO times AC over 2. What is the value of AO? AO equals to 5 units. And AC equals to 5 times root 3 over 2. So the area of triangle AOC equals to 5 times root 3 over 2. That is to say, the area of triangle AOC equals to 5 times 5 is 25 times root 3 over 2 square units, okay? Again, the area of triangle AOC equals to 25 times root 3 over 2 square units. But we have already proved that triangle AOC is congruent to triangle BOC. Therefore, they have the same areas. Because of the fact that triangle AOC is congruent to triangle BOC, they have exactly the same areas. So the area of quadrilateral ABCO will be equal to the area of triangle AOC plus triangle BOC. But because of the fact that the area of triangle AOC is equal to the area of triangle BOC, we can say that the area of quadrilateral ABCO equals to the area equals to 2 times the area of triangle AOC, because the area of triangle AOC equals to triangle BOC. So the area of quadrilateral ABCO will be equal to 2 times the area of triangle AOC. Okay. Again, the area of quadrilateral ABCO will be equal to 2 times the area of triangle AOC. Okay? But first of all, we will find out the area of triangle AOC. We actually found out that the area of triangle AOC equals to 25 times root 3 over 2. Okay? So we will multiply the area of triangle AOC by 2 in order to get the area of quadrilateral ABCO. Okay, so the area of triangle AOC times 2 will be equal to 2 times 25 root 3 over 2. Again, 2 times the area of triangle AOC equals 2 times 25 times root 3 over 2. Here, 2 over 2 is 1. So we got that the area of quadrilateral ABCO equals to 25 times root 3. The area of quadrilateral ABCO equals to 25 times root 3 square units. But so we have the area of quadrilateral ABCO. But what is the area of the green shape? The area of the green shape will be equal to the area of quadrilateral ABCO minus the area of sector AOB. Again, the area of quadrilateral ABCO minus the area of sector AOB will be equal to the area of the green shape. So I will write it down. The area of triangle ABCO, that is actually 25 times root 3 square units, minus the area of sector AOB will be equal to the area of the green shape. Okay, so the only thing that is left to do is to find out the area of sector AOB. Okay, and it is very simple to find out the area of sector AOB. What is the area of sector AOB? The area of sector AOB equals to pi times r squared, that is the area of the circle. We know that r equals to 5 units, times 120 degrees over 360 degrees. Again, the area of sector AOB equals to pi times r squared, that is the area of the circle, times 120 degrees over 360 degrees. 120 degrees over 360 degrees is 1 over 3. So we get here that it equals to pi times r squared over 3. R equals to 5. 5 squared is 25. So 25, we'll get that it is 25 pi over 3. The area of sector AOB equals to 25 pi over 3 square units. Again, we found that the area of sector, the area of the green shape equals to the area of quadrilateral ABCO minus the area of sector AOB. And the area of sector ABCO equals to 25 times root 3 square units, and the area of sector AOB equals to 25 pi over 3. Okay, so the area of the green shape equals to the area of quadrilateral ABCO minus the area of sector AOB. That is to say, it equals to 25 root 3 minus 25 pi over 2 square units. Okay? Again, the area of the green shape equals to the area of quadrilateral ABCO minus the area of sector AOB. That is to say, it equals to 25 times root 3 minus 25 pi over 2 square units. So that was the first method to find out the area of the green shape that equals to 25 times root 3 minus 25 pi over 2 square units. Okay. In the next step, we will find out the area of this green shape in a second method. We will find out the area of the green shape in a second method. First of all, we will define the center of the circle at point O, and we will join together points A and O by a straight line. AO is the radius of the circle that equals to 5 units, as we did in the first method, and BO is also the radius of the circle that equals to 5 units. And we also know that BC equals to AC according to two tangents theorem, that states that the lengths of two tangents from a common external point to a circle are equal. So BC equals to AC and AO equals to BO. Both of those two line segments are the radiuses of the circle, and we will join together points C and O by a straight line. So triangle AOC is congruent to triangle BOC. I will repeat very quickly why those two triangles can go into each other. AO equals to BO. AC equals to BC according to two tangents theorem. And OC equals to OC, it is a common angle. OC equals to OC, so we proved that all the sides of triangle AOC are equal to all the sides of triangle BOC. Therefore, those two triangles can go into each other according to side rule. And from the fact that triangle AOC can go into triangle BOC, we can derive that those two angles, angle ACO is equal to angle BCO. So if one angle is X, the other angle is also X. So 2X equals to 60 degrees according to what is given us the question. And if we divide the equality by 2, we will get that angle ACO equals to 30 degrees, and also angle BCO equals to 30 degrees. Actually, we did this in the first method, so I repeated on these steps very quickly. And we know also that this angle is 90 degrees, this angle is also equals to 90 degrees. Therefore, we know that in triangle, the right triangle AOC, that tangents 30 degrees equals to AO over AC, and we know that AO equals to 5 units. From this equality, we will get that AC equals to 5 times root 3. AC equals to 5 times root 3. AC equals to 5 times root 3. And according to two tangents theorem, AC equals to BC, so BC also equals to times root 3, 5 times root 3. And in the next step, we will extend line segment CO until it touches the circle at point H. We extend that line segment CO until it touches the circle at point H. In the next step, we will draw tangent to the circle at point H. Actually, edge O is the radius of the circle because of the fact that it exists from the center of the circle and ends at point H, that is a point on the circle itself. And we know that the radius and the tangent are perpendicular to each other. Again, a tangent to a radius is perpendicular, a tangent is perpendicular to a radius that is drawn to its tangency. So this angle is 90 degrees and this angle is also 90 degrees. So in the next step we will extend CA until it intersects with the tangent. We extended CA until it intersects with the tangent. The intersection point will be defined as point P, and we will also extend line segment CB or side CB until it intersects with the tangent edge. The intersection point between CB and the tangent edge will be defined as point Q. Okay, so here we have triangle, the big triangle, triangle CPQ. We will focus on the right triangle, triangle CHQ. On the right triangle, triangle CHQ, triangle CHQ is a right triangle because angle CHQ equals to 90 degrees. So we actually know this angle is equals to 30 degrees, this angle equals to 90 degrees. So in triangle CHQ we have angles that equals to 30 degrees plus angle that equals to 90 degrees plus angle CQH plus the size of angle CQH must be equal to 180 degrees according to the rule that the sum of the angles in any triangle equals to 180 degrees. Again, in triangle CHQ we have angle that equals to 30 degrees, angle that equals to 90 degrees, plus the size of this angle. The sum of those three angles must be equal to 180 degrees. So here we have 30 degrees plus 90 degrees plus the size of angle CQH must be equal to 180 degrees. 30 degrees plus 90 degrees is 180 degrees. So 180 degrees plus angle CQH equals to 180 degrees. So we will subtract 180 degrees from this equality and we will get that the size of angle CQH equals to 180 degrees minus 120 degrees, that is to say to 60 degrees. So angle CQH equals to 60 degrees. Okay, we will repeat on the same process on the left side. On this side, again we focus on triangle CHP. In triangle CHP, we know that the sum of the angles in any triangle equals to 180 degrees. Therefore, especially in triangle CHP, the sum of the angles must be equal to 180 degrees. So here we have 30 degrees plus 90 degrees plus the size of angle CPH must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle equals to 180 degrees. Again, the sum of the angles in the right triangle, triangle CPH, must be equal to 180 degrees. Again, the sum of the angles in the right triangle, triangle CPH, must be equal to 180 degrees. That is to say, 30 degrees plus 90 degrees plus angle CPH must be equal to 180 degrees. So here we have 180 degrees plus angle CPH equals to 180 degrees. We will subtract 180 degrees from this equality, and we will get that the size of angle CPH is actually 180 degrees minus 120 degrees is 60 degrees. Okay? So angle CPH equals to 60 degrees. So all the angles of triangle CPQ are equal to 60 degrees. That is to say, triangle CPQ is an equilateral triangle. Okay, triangle CPQ is an equilateral triangle. Triangle CPQ is an equilateral triangle, and what is the area of triangle CPQ? We know that we have a rule that states that the center the rule states that the center of a circle inscribed in a triangle is the incenter of the triangle. So I will read the rule again. The rule states that the center of a circle inscribed in a triangle is the incenter of the triangle. So here we have equilateral triangle, and inside the equilateral triangle CPQ we have a circle that is inscribed inside it. So according to the rule that is stated, the center of triangle CPQ is the same center of the circle that is inscribed inside the triangle. So the center of the circle is at point O, so the center of triangle CPQ will be also at point O. Okay, again, the center, according to the rule that is stated, we can derive that the center of equilateral triangle CPQ is at point O. Okay? The center of the equilateral triangle CPQ is at point O. That is the center of the circle also. And we have another rule. The rule states that the height from the center of an equilateral triangle crosses the side. Crosses the side. Okay, again, the rule states that the height from the center of an equilateral triangle crosses the side. So we know that the center of our equilateral triangle CPQ is at point O, and as you can see from the drawing, we have from point O three heights to the three sides of the equilateral triangle CPQ. And according to the rule that is stated, this height OB to side CQ of the equilateral triangle crosses the sides. That is to say, CQ equals to BQ. Okay, according to the rule that I stated, CB equals to BQ. CB equals to BQ. According to the rule that is stated, CB equals to BQ, but CB equals to 5 times root 3, so CB will be also, QB will be BQ, or will be also equal to 5 times root 3. And also, we know that the height OA that exists from the center of the equilateral triangle crosses the side AC. That is to say, AC equals to AP, and if AC equals to 5 times root 3, AP will be also equal to 5 times root 3. And we know that all the sides of an equilateral triangle are equal to each other, So the size of side CP is 5 root 3 times plus 5 root 3 is 10 root 3. So the size of PQ also will be equal to 10 times root 3 but according to the rule that is stated that the height from the center of the equilateral triangle crosses the side PH equals to HQ. PH equals to HQ. So if PH equals to X, then HQ will be also equal to X. So PH plus HQ will be equal to 2X. PH plus HQ will be equal to 2X. And we know that 2X equals to 10 times root 3. Okay, so we got here the equality that 2x equals to 10 times root 3. If we divide this equality by 2, we will get that x equals to 5 times root 3. X equals to 5 times root 3. So here x equals to 5 times root 3, and here x equals to 5 times root 3. Okay? And we know if we have triangle ABC, we know that the size of AB is A, the size of AC is B, and the angle between AB and AC is theta. Then the area of this triangle equals to A times B times sine theta over 2. Again, the area of this triangle equals to A times B times sine theta over 2. So, according to this formula, the area of the equilateral triangle CPQ, the area of the equilateral triangle CPQ will be equal to CP times CQ times sine 60 degrees over 2. Again, the area of the equilateral triangle CPQ according to the formula that I showed you, the area of triangle CPQ will be equal to CP times CQ times sine 60 degrees over 2. But CP equals to CQ equals to 10 times root 3. So it will be 10 times root 3 square, and sine 60 degrees is root 3 over 2. And we have, again, sine 60 degrees is root 3 over 2, but we have we must divide root 3 over 2 by 2. So it will be root 3 over 4. So the area of equilateral triangle CPQ will be equal to 10 times root 3 squared times root 3 over 4. 10 times root 3 squared is 300. Okay? We get here 300 times root 3 over 4. And 300 over 4 is 75 over 3. So the area of triangle CPQ equals to 75 times root 3 square units. Okay? The area of the equilateral triangle CPQ equals to 75 times root 3 square units. Okay? And what is the area of the circle? The area of the circle equals to pi r squared. Again, the area of the circle equals to pi r squared. The area of the circle equals to pi r squared. R equals to 5, so r squared is 5 squared. 5 squared is 25, so the area of the circle is 25 pi. So the area of triangle CPQ minus the area of the circle will be equal to the area of the green shape plus the area of the yellow shape plus the area of the blue shape. Again, the area of the big triangle CPQ minus the area of the circle will be equal to the area of the green shape plus the area of the yellow shape plus the area of the blue shape. Okay, so the area of triangle CPQ minus the area of the circle will be equal to the area of the green shape plus the area of the yellow shape plus the area of the blue shape. Okay, so we have this formula that states that the area of the big triangle CPQ minus the area of the circle equals to the area of the green shape plus the area of the blue shape plus the area of the yellow shape. You can see it from the drawing that the area of the big triangle minus the area of the circle equals to the area of the green shape plus the area of the yellow shape plus the area of the blue shape. Okay, so the area of triangle CPQ equals to 75 times root 3 minus the area of the circle that equals to 25 pi. So the area of the triangle minus the area of the circle equals to the area of the green shape plus the area of the yellow shape plus the area of the blue shape. Okay. The area of triangle CPQ minus the area of the circle equals to the area of the green shape plus the area of the yellow shape plus the area of the blue shape. Okay. But as you can see from the drawing, those three shapes are identical. They have two sides that both of them are equal to 5 times root 3, 5 times root 3, 5 times root 3, 5 times root 3, 5 times root 3. And the angle between those two sides are 60 degrees in all the three shapes. So therefore their areas are also equal to each other. The areas of the three shapes, the green shape, the yellow shape and the blue shape, the areas are equal to each other because they have exactly the same shape. That is to say, if we divide the sum of the sum of the areas of the three shapes by 3, we will get the area of each shape, or we will get the area of the green shape. Okay, so we will divide the total areas of the three shapes by 3, and we will get the areas of each shape, and especially we will get the area of the green shape. Okay, so here we have this expression. Actually, it is the sum of the areas of the three shapes, and we know that the area of the three shapes are equal to each other. So if we divide the areas of the sum of the areas of the three shapes by 3, we will get the area of the green shape. So the only thing that is left to do is to divide the sum of the areas of the three shapes by 3, and we will get the area of the green shape. So the area of the green shape will be equal to 75 times root 3 minus 25 pi over 3. Okay? The area of the green shape equals to the sum of the areas of the three shapes divided by 3, because the areas are equal to each other. So if we divide the total sum of the areas by 3, we will get the area of each shape, and especially the area of the green shape. Okay, so we divided the total area of the three shapes by 3, And in this way we got the area of the green shape. So this expression is the area of the green shape. Okay, we'll simplify this expression, and we will get that 75 over 3 is 25. So we found out that the area of the green shape equals to 25 times root 3 minus 25 pi over 3. Again, the area of the green shape equals to 25 times root 3 minus 25 pi over 3 square units. Okay? Okay, so we finished with the second method. So in the next step I will present to you a third method to find out the area of this green shape. Okay, we will join together points A and B by a straight line. And we will define the center of the circle as point O, and we will join points A and O by a straight line, and we will join together points B and O by a straight line. AO is the radius of the circle that equals to 5 units. BO is the radius of the circle that equals to 5 units. And actually we know that AC equals to BC according to two tangents theorem. If we draw two tangents from a common external point, therefore to a circle, therefore they are equal to each other, and we have the rule that in front of equal sides in triangle ABC we have equal angles. So this angle equals to this angle, because those two angles are located in front. Those two angles are located in front of equal sides. AC equals to BC. So, and if we define this angle as x, then this angle will be also equal to x. And we know that the sum of the angles in triangle ABC equals to 180 degrees, therefore 60 degrees plus x, that is 2x, equals to 180 degrees. Okay, we have this equality that states that 60 degrees plus 2x equals to 180 degrees. If we will subtract 60 degrees from this equality, and we will get that 2x equals to 180 degrees. 180 degrees minus 60 degrees is 180 degrees. 2x equals to 180 degrees. We divide this equality by 2 and we will get that x equals to 60 degrees. Okay, so x equals to 60 degrees. We substitute x by 60 degrees. So triangle ABC has three angles that are equal to 60 degrees. Therefore, triangle ABC is an equilateral triangle. Triangle ABC is an equilateral triangle. Okay, we know that triangle ABC is an equilateral triangle. Then we will join together points C and O. And we also know that the radius creates 90 degrees with its tangent CB, so this angle is 90 degrees. This angle is also equals to 90 degrees. So here we know that the sum of the angles in a quadrilateral equals to 360 degrees. So we have here 60 degrees plus 90 degrees plus 90 degrees is 240 degrees, and in order to complete the sum of the angles in quadrilateral ABCO to 360 degrees, this angle must be equal to 120 degrees. And we will join together point C and O by a straight line. And again, we will prove that triangle AOC is congruent to triangle BOC. We will focus on triangle AOC and triangle BOC. Okay, so on triangles, we will focus on triangle AOC and triangle BOC. So I did it in the previous methods. I will repeat it quickly. I'll repeat on it quickly. AO equals to BO equals to the radius. AC equals to BC according to two tangents theorem. And OC equals to OC. It is a common angle. It is a common side. OC equals to OC. So we actually proved that all the sides of triangle AOC are equal to all the sides of triangle BOC. Therefore, they congruent to each other according to side rule. And from the fact that those two triangles congruent to each other, we can derive that those two angles are equal to each other. So if one angle equals to x, then the other angle also equals to x. So the sum of those two angles are 2x. And we know that 2x must equal to 60 degrees. And if we divide this equality by 2, we will get that angle BCO equals to 30 degrees, and angle ACO also equals to 30 degrees. Okay, so in the right triangle, triangle AOC, in the right triangle, triangle AOC, we know that tangent 30 degrees equals to AO over AC. Again, tangent 30 in the right triangle, triangle AOC, tangent 30 degrees equals to AO over OC. But we know that AO equals to 5 units. So we substitute AO by 5. This is the radius of the circle, 5 over AC. So tangent 30 degrees equals to 5 over AC. From this equality we can derive that AC equals to 5 times root 3. AC equals to 5 times root 3. AC equals to 5 times root 3. We know that AC equals to BC according to two tangent theorem, so BC also equals to 5 times root 3. And we already proved that triangle ABC, it is equilateral triangle, it has all its angles that equals to 60 degrees. Therefore, according to the formula that I presented to you for the area of the triangle, the area of triangle, the right triangle, the equilateral triangle, triangle ABC, will be equal to 5 times root 3 square times root 3 over 4. Again, the area of equilateral triangle, triangle ABC, will be equal to 5 times root 3 square times root 3 over 4. So 5 times root 3 square is 75 times root 3 over 4, and we know that the area of the green shape equals to the area of triangle ABC minus the area of the circular segment AB. So the area of triangle ABC minus the circular segment AB will be equal to the area of the green shape. Again, the area of the green shape equals to the area of triangle ABC minus the area of the circular segment AB. Okay? But what is the area of circular segment AB? The area of circular segment AB equals to the area of sector AOB minus the area of triangle AOB. And the area of sector AOB equals to pi times r squared times 120 degrees over 360 degrees and the area of triangle ABC according to the formula that I presented to you will be equal to 5 times 5 times sine 120 degrees over 2. Okay, so the area of circular segment AB will be equal pi times r squared, r equals to 5, so pi times r squared is 25 pi, and 120 degrees over 360 degrees is 1 over 3, so it is 25 pi over 3 minus 25 sine root 3 over 4. Okay, so the area of circular segment AB equals to 25 pi over 3 minus 25 root 3 over 4. And the area of the green shape equals to the area of triangle ABC, that is ABC minus the area of circular segment AB. Again, the area of the green shape equals to the area of triangle ABC minus the area of circular segment AB. The area of triangle ABC minus the area of circular segment AB equals to the area of the green shape. We have already found out that the area of triangle ABC equals to 75 times root 3 over 4. And the area of circular segment AB equals to 25 pi over 3 minus 25 root 3 over 4. So the area of the green shape equals to this expression. We will open the brackets here and we will get that 75 root 3 plus 25 root 3 is 100 root 3 over 4 minus 25 pi over 3. So it equals to 1 over 4 is 25 root 3 minus 25 pi over 3. So the area of the green shape equals to 25 times root 3 minus 25 pi over 3 square units. Okay? According to the third method, the area of the green shape equals to 25 times root 3 minus 25 pi over 3 square units. Okay? So now I will summarize the lecture. So actually we wanted to find out the area of the green shape, and we found out the area of the green shape in 3 different ways. In the first method, we defined the center of the circle as point O. We join together points O and B by a straight line. OB is the radius of the circle. We join together points A and O by a straight line. We know that BC is tangent to the circle at point B, and AC is tangent to the circle at point A. And we have a rule that a tangent to the circle is perpendicular to the radius drawn to its tangency. So here we have tangent BX to the circle at point X, and the radius that is drawn to the tangent point, that is to say to point X, will be perpendicular to the tangent BX. So here we have tangent BC, and the radius is drawn to the point of tangency, that is to say to point B. Therefore, the radius is perpendicular to its tangent, that is to say this angle equals to 90 degrees. And also here we have the radius that is drawn to the point of tangency, that is to say to point A. Therefore the radius is perpendicular to the tangent, that is to say this angle equals to 90 degrees. Okay, and we have also second rule that talks about two tangents theorem. Two tangents theorem states that the lengths of two tangents from a common external point to a circle are equal. So, according to two tangents theorem, if you have external point to this circle, that is to say point P, and from point P you draw two tangents to this circle, then the lengths of those two tangents are equal to each other. That is to say SP equals to PM. And according to two tangents theorem, we have from external common point, point C, we draw two tangents to this circle, tangent BC and tangent AC. Therefore, according to two tangents theorem, the lengths of those two tangents are equal to each other. That is to say BC equals to AC. Okay, and then we focused on triangle AOC and triangle BOC. We proved that those two triangles are congruent to each other because we have BO equals to AO. Both those two line segments are the radiuses of this circle, therefore they are equal to each other. We know that BC equals to AC according to two tangents theorem, and OC is a common side. It belongs to both triangles, so OC equals to OC. So we proved that all the sides of triangle OBC equals to all the sides of triangle OAC. Therefore, they are congruent to each other according to side rule. Okay, and from the fact that they are congruent to each other, we can derive that angle BCO equals to angle ACO. So if this angle is x, this angle also will be x. So the sum of those two angles, 2x, must be equal to 60 degrees. If 2x equals to 60 degrees, if we divide this equality, we get that x equals to 30 degrees. So this angle is 30 degrees, and this angle is also 30 degrees. Okay? And we have ruled that the sum of the angles inside the quadrilateral equals to 360 degrees. So in quadrilateral ABCO, the sum of the angles must be equal to 360 degrees. That is to say, 60 degrees plus 90 degrees plus 90 degrees plus the size of this angle must be equal to 360 degrees. Okay? So we have this equality that states that the sum of the angles in triangle in the quadrilateral ABCO equals to 360 degrees. Okay? So from this equality we got that the size of angle AOB equals to 120 degrees. The size of this angle equals to 120 degrees because it completes the sum of the angles in the quadrilateral ABCO to 360 degrees. Okay? And in triangle AOC, we know that tangent 30 degrees equals to AO over AC. Okay? Tangent 30 degrees equals to AO over OC, that is 5 over OC because AO equals to 5. And we know that tangent 30 degrees equals to 1 over root 3. So from this simple equality we got that AC equals to 5 times root 3. And the area of triangle AOC, this triangle equals to the base of the triangle times the height over 2. The base is AO, that equals to 5 units, and the height is AC, that equals to 5 times root 3. Okay, so we multiplied one by each other and we got that the area of triangle AOC equals to 25 times root 3 over 2. But because of the fact that we proved that triangle AOC is congruent to triangle BOC, the area of triangle, the area of quadrilateral ABCO will be equal to the area of triangle AOC plus the area of triangle BOC, but the two areas are equal to each other because those two triangles can go into each other. So the area of triangle, the area of quadrilateral ABCO will be equal to 2 times the area of triangle AOC. Okay, the area of quadrilateral ABCO equals to 2 times the area of triangle AOC because triangle AOC is congruent to triangle BOC. So we can substitute the area of triangle BOC by the area of triangle AOC. So the area of quadrilateral ABCO equals to 2 times the area of triangle AOC. Okay? So we multiplied the area of triangle AOC by 2, and we got the area of quadrilateral ABCO that is equals to 25 times root 3. And so the area of quadrilateral ABCO equals to 25 times root 3 square units. And what is the area of the green shape? The area of the green shape equals to the area of quadrilateral ABCO minus the area of sector AOB. Okay, the area of the green shape equals to the area of quadrilateral ABCO minus the area of sector AOB. And what is the area of sector AOB? The area of sector AOB equals to pi r squared, that is the area of the circle, times 120 degrees minus 360 degrees. We know that the radius of the circle equals to 5 units. So we have all the data, and we found out that the area of sector AOB equals to 25 pi over 3, and we have already found out that the area of quadrilateral ABCO equals to 25 times root 3. So the area of quadrilateral ABCO minus the area of sector AOB that equals to 25 pi over 3 will be equal to the area of the green sector. Okay? So the area of the green sector equals to 25 times root 3 minus 25 pi over 3 square units. So that is the first method to find out the area of the green sector. Then we found the area of the green sector in a second method. We actually connected point C and O together by a straight line. Then we extended CO until it touches the circle at point edge, and at point edge we draw tangent to the circle, and then we extended AC until it intersects with the tangent, and at point P we extended CB until it intersects with the tangent at point Q. Okay? And then we actually proved again that triangle AOC can go into triangle BOC, because AO equals to BO, AC equals to BC according to two tangents theorem, and OC equals to OC. It is a common side. So therefore triangle AOC is congruent to triangle BOC according to side rule. Therefore angle ACO equals to angle BCO, and if one angle is x, then other angle is also x, so 2x must be equal to 60 degrees. We divided this equality by 2 and we got that this angle is 30 degrees and this angle also equals to 30 degrees. Then we know that the tangent QP is tangent to the circle at point H, and O edge is the radius. So we have the rule that the tangent is perpendicular to the radius that is drawn to the point of tangency. Therefore this angle is 90 degrees and this angle is also 90 degrees. So we have in triangle CPH one angle that is 30 degrees, the other angle is 90 degrees, so the third angle must be equal also to 60 degrees in order to complete the sum of the angles in triangle PCH to 180 degrees. We repeated on the same process exactly on the other side, and in this way we found out that this angle also equals to 60 degrees. Therefore triangle CPQ is an equilateral triangle. Okay? And we have a rule that the center of a circle inscribed in a triangle is the incenter of the triangle. So the center of the circle O is also the center of the equilateral triangle, triangle CPQ, according to the rule that I stated. And we have also the second rule that states that the height from the center of an equilateral triangle crosses the side. So we have here three heights from point O, that is the center of the equilateral triangle, according to the rule that I stated, the height crosses the side to two equal parts. So OA divides CP to two equal parts. So if this angle equals to 5 times root 3, this angle must be also equal to 5 times root 3. And the same rule here. We have from the center of the equilateral triangle, we draw height to CQ, therefore CB will be equal to CQ. So if CB equals to 5 times root 3, then PQ also must be equal to 5 times root 3. And here we have equilateral triangle, so if one side equals to 10 times root 3, then this side must be also equals to 10 times root 3. And according to the rule that the height divides the side to two equal parts, when we know that PQ equals to 10 times root 3, then if we divide it to two equal parts, PH will be equal to 5 times root 3, and HQ also will be equal to 5 times root 3. Okay? And so now we know that the side of equilateral triangle CPQ equals to 10 times root 3. And we know that the area of this triangle equals to A times B times sinus theta over 2. So according to the formula that I presented to you, the area of equilateral triangle CPQ will be equal to CP times CQ times sine 60 degrees over 2. Okay? The area of equilateral triangle CPQ will be equal to CP times CQ times sine 60 degrees over 2. But CP equals to CQ equals to 10 times root 3, so CP times CQ is actually 10 times root 3 squared, and sine 60 degrees is root 3 over 2. Root 3 over 2 over 2 is root 3 over 4, so in total we got that 10 times root 3 squared times root 3 over 4 is the area of triangle CPQ. We solved this simple equation and found that the area of equilateral triangle CPQ equals to 75 times root 3 square units. So the area of the circle is pi r square. R equals to 5, so pi r square will be equal to 25 pi. And the area of the big triangle CPQ minus the area of the circle equals to the area of the green shape plus the area of the yellow shape plus the area of the blue shape. Okay, the area of the green shape equals to the area of triangle CPQ minus the area of the circle. Okay, so we know that the area of the triangle CPQ equals to 75 times root 3, and the area of the circle equals to 25 pi. So the area of the three shapes equals to 75 times root 3 minus 25 pi. Okay? But as you can see from the drawing, those three shapes are identical and they have exactly the same sides, and the angle between those two sides are equal. So because of the fact that they are identical, they have also the same areas. So if we divide the total sum of the areas of the three shapes by 3, we will get the area of one shape. So if we divide the total sum of the areas of the three shapes by 3, we will get the area of the green shape. So the area of the green shape will be equal to the area of the total sum of the three shapes divided by 3. So we divided the total sum of the areas of the three shapes by 3, and we got the area of the green shape. That is to say, the area of the green shape equals to 25 times root 3 minus 25 pi over 3 square units. Okay? So that was the second method in finding out the area of the green shape, this green shape. So in the next step I will present to you a third method to find out the area of the green shape. Actually, we define the center of the circle as point O. We connected point A and O. This angle is 90 degrees. We connected points O and B. This angle is 90 degrees. According to what I proved in the previous methods. And we know that AC equals to BC according to two tangents theorem. And actually we connected points A and B together by a straight line. We know that this angle equals to 60 degrees and AC equals to BC according to two tangents theorem. And we have the rule that in front of equal sides in the triangle there are equal angles. So this angle equals to this angle in triangle ABC. So, and we know that this angle equals to 60 degrees. So the sum of those two angles must be equal to 120 degrees, and 120 degrees must be equal to 2x. And if we divide this equality by 2, we get that x equals to 60 degrees. So this angle equals to 60 degrees, and this angle also equals to 60 degrees. Therefore, triangle ABC is an equilateral triangle. Okay? So, again, we proved that triangle AOC is congruent to triangle BOC, because AO equals to BO is the radius of the circle, AC equals to BC according to two tangents theorem, and OC equals to OC, it is the common side. So triangle AOC is congruent to triangle BOC according to side rule. Therefore, those two angles are equal to each other, and if the sum of those two angles is 60 degrees, each of them must be equal to 30 degrees. So in triangle ACO, we know that triangle 30 degrees equals to AO times AC. AO equals to 5. So triangle 30 degrees equals to AO over AC. AO equals to 5 units. We know that triangle 30 degrees equals to 1 over root 3. So from this equality, simple equality, we got that AC equals to 5 times root 3. Okay? So the area of equilateral triangle ABC will be equal to 5 times root 3 squared times root 3 over 4, because that is the area, that is the formula for the area of any equilateral triangle, that is x squared times root 3 over 4 if x is the size of one of its sides. Okay, so we found out that the area of triangle ABC equals to 75 times root 3 over 4, and the area of triangle ABC minus the area of circular segment AB will be equal to the area of the green shape. But what is the area of circular segment AB? It is equals to the area of the sector AOB minus the area of triangle AOB. And what is the area of sector AOB? It equals to the area of triangle A, the area of sector AOB equals to pi times r squared times 120 degrees over 360 degrees, and the area of triangle AOB equals to 5 times 5 times sinus 120 degrees over 2. So the area of circular segment AB equals to 25 pi over 3 minus 25 root 3 over 4. Okay, so the area of triangle ABC minus the area of circular segment AB will be equal to area of the green shape. The area of triangle ABC minus the area of circular segment AB will be equal to the area of the green shape. We have already found out that the area of triangle ABC equals to 75 times root 3 over 4, and the area of circular segment AB equals to this expression. We solved this simple expression, and we found out that the area of the green shape equals to 25 pi minus 25 pi over 3 square units. Okay? Thank you very much.